I see the flying car industry as game changing when it comes to not only future warfare, but future military operations, just as important, humanitarian relief operations, hurricane support, all the things that we do defense of the homeland. If you start thinking about these devices as nodes in a network, it fundamentally changes the game.
Agility Prime is a program with a vision of world impact. By partnering today with stakeholders across industries and agencies, we can set up the United States for this aerospace phenomenon. Potential outcomes are rewarding and transformative with both military and commercial applications.
I want to offer my congratulations to Dr. Roper and his team for achieving this revolutionary rapid contracting and prototyping method to bring industry and DoD together to develop this new exciting technology with both military and civilian applications. This technology will have great benefit to the needs that we have in Alaska and the Arctic, where conventional aircraft, vehicles, and vessels oftentimes can't operate.
Agility Prime is part of our Defense Department's long history of turning futuristic ideas into reality. I'm proud that the federal government is investing in evolutionary ideas. Agility Prime is leading the way.
This launch of Agility Prime is so exciting. This technology has the potential to make vertical flight more affordable and more widely available. And with the encouragement of the U.S. Air Force and the entire federal government, American companies employing American workers can gain a head start and win a fair share of this lucrative market. Evtols have the same agile, vertical takeoff and landing capability as helicopters, but are quieter and should cost much less to operate because of their electric motors.
We are becoming a trusted innovation partner in commercial tech. I could not be prouder of this initiative. I could not be prouder of this team. And I am excited to see how quickly we can go to help commercialize this market for our nation so that our warfighters have options they don't have today, and our nation has an economic advantage far into the future. Innovation is a battlefield, and Agility Prime is just one way we're going to win it.
Agility Prime seeks to ensure a global advantage in advanced logistics technology. Agility Prime can reduce the risk of adversary commercial dominance, resulting in military disadvantage. As the United States Air Force looks at generating combat power away from runways, those distributed logistics aircraft must be runway independent. This new transformative capability is a promising opportunity to conduct that mission in an affordable and a scalable manner.
Today, we gather for Agility Prime to drive transportation innovation, lower barriers to entry, and expand our partnerships.
We see a time when automation technologies make the requirements on the pilot much less. And we see flying as being accessible to a much wider range of people.
It is truly a great credit to Agility Prime that could put on this virtual event with so many hometowns of the United States represented. You know, industrial base is not really about just what a country can make. More than that, it's about the people who dream up what to make. And then, of course, those people who make it.
Hello, everyone, and welcome back to our webinar series after the Team Up event. I'm Major Phil Hahn, here for Colonel Diller to facilitate today's webinar. I'd like to start things off by congratulating the AFWERX team on being selected by Fast Company as the number 16 best workplace for innovators. This is a great honor to be recognized with the likes of Google and Amazon and some of the most successful companies in the world. I'm proud to be part of the AFWERX team that is going places and making a difference. I hope you all found the Team Up event useful in understanding our mission here at AFWERX and Agility Prime for creating great relationships as we move forward with the STTR proposals. Speaking of those proposals, as of today, there are 10 days left before the deadline for those proposals. There is still time to put together a proposal for the research funding opportunity focused on Evtol and associated technologies. Later today, we will be hearing from Major Jared Evans from AFWERX Ventures and Dennis Andhurst from the Wright Institute on the proposal process, tips and tricks, along with a Q&A opportunity. But first, we will kick off the day with our speaker. He will be speaking today on battery applications to Evtol, infrastructure, and future trends. Matthew Kaiser joined NREL in 1992 and today manages the Electrochemical Energy Storage Group in the Center for Integrated Mobility Sciences. This group includes the energy storage team, which conducts modeling, simulation, and systems evaluation activities to assess and optimize energy storage components at the materials, cell, pack, and systems levels, as well as the power electronics team, which develops power electronics and electric motor technologies with greater dependability, efficiency, and durability. As we're going through the presentation, feel free to submit questions in the chat for the Q&A following the presentation. Matt, thanks for being here, and I look forward to the presentation.
All right, thanks a lot, Phil. Let me share my screen. All right, hopefully everyone can see my screen. Again, my name is Matt Kaiser. I'm the Electrochemical Energy Storage Group Manager at the National Renewable Energy Laboratory, located in beautiful Golden, Colorado. I know these times are crazy, but once they're over, then please come and visit us. If you enjoy skiing, come and visit us in the wintertime. If you enjoy hiking or biking, come in the summertime. But we'd happy to be able to host you here at NREL. I come at energy storage from a unique perspective. When I started back in 1992, lead acid batteries were king, and they were going to be the technology used to be able to electrify vehicles. We soon found out that the cycle life and the energy density of those particular batteries was fairly poor. So we immediately moved on to NiCad, then to nickel hydrogen for a short period of time, then to nickel metal hydride, which was the first battery technology used in hybrid electric vehicles. I'm sure everyone knows here that was what was used in the Prius. And now we're at lithium and all versions of lithium. I know I get a lot of questions on the slide that you're seeing right now. And this is kind of the detail and the depth that we go to now to be able to optimize lithium battery systems. So what you see here is actually just an NMC particle that's 25 microns by 25 microns by 25 microns and has 25 million degrees of freedom. And the lines that you're seeing are basically the lithium pathways from the NMC to the anode during charging. And what we're trying to do here is trying to optimize the ionic pathways between the cathode and the anode in order to enable extreme fast charging. So we're getting down into the details of the battery system in order to be able to optimize them for the applications that are out there today. So this is the obligatory agenda. First, I'll go over the background. Then I'll touch on, state-of-the-art lithium-ion chemistries. I know what's important to you and what's important to me are the different cost targets and how we're going to be able to reduce the cost of different lithium chemistries that are out there today. I'll touch on that. I'll touch on different future battery systems. And then finally, I'm going to go through 3 different priorities in the aviation and the electric vehicle space. And that would be extreme fast charging, life and degradation. Who doesn't want more life? And then finally, safety. Obviously, safety is very important from an electric vehicle standpoint, but it's also very important for the eVTOL industry. So what is the most motivation for pursuing eVTOL? I think this graphic outlines it fairly well. Back in 2000, air transport consisted of, had about 2% of the CO2 emissions. However, it's estimated that by 2030, 3% of the CO2 emissions will be basically air transport will be responsible for 3% of the CO2 emissions. And what we're trying to do is we're trying to decrease that load and increase the environmental performance of electrified vehicles, besides all the other options that were given in the video that was just presented at the beginning of this talk. So electrified aircraft propulsion, this is how I see it right now. I actually borrowed this slide from Dr. Misra at NASA Glenn Research Center. Basically I have 3 different categories. So we have all electric, consisting of a battery system that feeds into an electric bus going to a motor that then powers different propellers, different fans. One topic on this particular area that people are interested in is combining 2 different battery systems. And this is something that we've worked on quite a bit at NREL and over the past years. And it's really combining an energy dense battery with a power dense battery. You get the power for the takeoff, in this particular case, but the energy battery is providing the energy for the cruising or at cruising altitude. One of the big problems that we've had in the past for electric vehicles, and I also see that this is going to be a problem for eVTOL, is trying to justify the cost, the mass, and the volume for 2 separate battery systems. It's going to be difficult to integrate both of those systems in order to be able to meet all those targets. The second area that batteries are going to be used in is basically a hybrid electric vehicle. So here you can see we have fuel feeding a turbofan. The turbofan is then connected to a generator, which then provides electric power through an electric bus to a battery. And so the generator and the battery feed electricity to the motors that then power the fans. Obviously, this is something that would be utilized primarily for takeoff on the battery system. But the nice thing about the generator is it can actually be used to charge the battery, and therefore you wouldn't actually need to charge the battery when it's actually on the ground. And finally, the final electric option that I see today is all turbo electric, basically fuel, once again, feeding a turbo shaft that's connected to a generator, and then the electric bus without the battery system then feeds the 2 different motors. The great thing about these particular technologies is it really reduces the maintenance, and as indicated in the video that we saw before, it actually does help with vertical takeoff and the elimination of runways out there for the most part. Now, the electrification has been in the news quite a bit over the last several years. The headlines in particular are talking about EV batteries. It's estimated that by 2030 that there are going to be over 22 electric vehicles on the road today, 22 million, that is 22 million electric vehicles on the road today. And that's actually a global EVs. And you can see here in the graph on the left, we have different applications, so passenger, commercial, EVs, stationary storage, consumer electronics, and then e-buses. For the most part, the growth over the next 10 years is primarily going to be focused on passenger EVs, and then followed closely by stationary applications. The one great thing about this is that the United States, whereas we did not have very many manufacturing facilities for lithium-ion batteries the last few years, we're starting to get those and develop those within the United States. And so GM and LG are investing $2.3 billion in Lordstown, which is in Lordstown, Ohio, which is going to be producing a 30 gigawatt hour cell plant. Tesla, as many of you know, has a gigawatt factory in Nevada. They're also developing a gigawatt factory in Texas, which is going to be even bigger. And SK Innovation, which is a South Korean company, is working with a number of battery OEMs, or original equipment manufacturers like Volkswagen and BMW, in order to be able to look at cells for those vehicles. And they're producing a plant in Commerce, Georgia, that's at 10 gigawatt hours. So the good news is that we're starting to get manufacturing facilities here in the United States, and it's basically going to be a requirement if we want to stay ahead of the game. So what are lithium-ion batteries? What is the technology? The batteries are actually fairly simple when you look at it. They have four primary components. They have the cathode, the anode, the separator, and the electrolyte. And basically what happens is you have ions that transfer from the anode to the cathode when it's discharging, and from the cathode to the anode when it's charging. And then the electrons go through the circuit. This could be any type of a load. This could be a laptop. This could be a cell phone. This could be the computer that I'm using right now. The one thing that I wanted to note is that lithium-ion batteries, there's a range of lithium-ion batteries, and you're going to have to choose the battery that's right for the application for you. But the voltage range for these batteries go from 2.2 to 4.2. Cycle life is anywhere between 1,000 and 5,000 cycles. Admittedly, you could probably get even more than 5,000 cycles if you're able to control the environmental condition. Something that's important to you and to me is the specific energy density of these. Basically, how much energy is stored within a kilogram of mass. And that energy density for right now is, for the most part, between 180 and 250 watt hours per kilogram. It depends on the cathode and anode you use, but you know, so some of those will actually fall outside of that range, but that's the typical range where lithium-ion batteries are today. From a volumetric energy density, on average, they're around 400 watt hours per liter, and the temperature range in which these batteries can be used are between -30 and 60 degrees C, but it should be noted that this is only for discharge and not charge. Typically, you don't like to go too far below -5 degrees C when charging the batteries. Otherwise, you're going to get lithium plating and capacity loss issues. So the different type of lithium-ion cell configurations out there, there's two primary ones. That would be cylindrical and prismatic. The cylindrical ones, I'm sure you're all aware of. It's much like the alkaline cells, the AA, the AAA batteries that we put into our electronics. In this particular case, it's just lithium. In order for you to be able to produce these type of cylindrical cells, it's fairly easy. You take two separators, a cathode and an anode, and then you wrap it around a mandrel to be able to generate the cylindrical cell. One great thing about cylindrical cells is that you can incorporate different safety technology in them, such as a current interrupt device, and you can also use them to have vents in the top and the bottom. One big problem with cylindrical cells is that the packing density is not that great. And that's the reason why most people are actually morphing from the cylindrical design over to the prismatic design that you see here on the right. And there's two types of prismatic designs, wound and stack layers, and they come in soft and hard cans. The soft pouch material is basically a mylar balloon. Typically when you fill the soft pouch material or the mylar material, what you do is you pull a vacuum on the system, compress all the layers together. The vapor pressure of the electrolyte is very low, so you can maintain that pressure in the system itself. But one of the big problems with this is that you can't, or it's been difficult to incorporate a vent in the system for safety purposes. And as cells age, typically what will happen is that the electrolyte will degrade. When the electrolyte degrades, then you produce gases. Those gases will then cause that mylar pouch to become a balloon. And I'm sure some of you have seen this with the power electronics that you have out here outside. But you know, at your place, at your home, or at your industry, basically you can see that the mylar pouch actually blows up and becomes a bit of a balloon at that point in time. And so that's the reason why a lot of people are going to the hard prismatic cases. The energy density is much better for the soft pouch cells, but people are going to the hard cans because you can incorporate a vent in those cans, and it takes pressure fairly well. And So for those two issues, most people are actually going to the hard can, a wound stack layer that's put into a hard case. Now, I get a lot of questions on this about energy and power cells. In general, it's not the chemistry that determines whether or not it's a power or an energy cell. What really determines it is the design of the cell. And so what you can see here is two different designs. And for your reference, this is a bit of an exaggeration. But on the left, we have an energy cell, and on the right, we have a power cell. Both of these are at the same voltage. You can choose any chemistry out there. For this particular one, we'll say this is LCO graphite or lithium cobalt oxide and graphite. And basically, energy cells, which are on the left, have more active material and less inactive material. The active material would be the cathode and the anode. The inactive material would be like the aluminum current collector and the copper current collector that you see here. Now on the right is the power cell. The power cell has many more current collectors, aluminum and copper current collectors, and the thickness of the cathode and anode is much smaller. And the reason why we do that is because the diffusion length, basically for the ion to go from the cathode to the anode or vice versa, is much shorter in a power cell than in an anode. Therefore, you can discharge the energy much quicker in a power cell versus an energy cell. And so really the only difference here is the thickness of the cathode and the anode, and the fact that power cells have more inactive material, such as current collectors. I did put up here different thicknesses for energy and power cells. These should be taken with a grain of salt because some people would say that the difference is at 25 microns, others would say 100 microns. But in general, an energy cell has cathode and anode thicknesses that are greater than 75, and power cells have cathode and anode thicknesses that are less than 50 microns. So lithium-ion chemistries, they're very varied. I have many people come to me and say, you know, give me a lithium battery, and then I'm like, well, what battery do you want? It's very similar to going into an ice cream shop and saying, give me an ice cream cone. Of course, they'll look at you and say, you know, do you want chocolate, Rocky Road, vanilla? What type do you want? And these are the most popular ones on the market today, and I've ranked them at 6 different metrics. I'm going to highlight a couple of them. The graphite LCO, or the lithium cobalt oxide graphite system, is what's in most consumer electronics today. So this is what's in your laptop, this is what's in your cell phone, this is what's in your tablet. The one big ding for LCO graphite systems is that they have very high energy density, but unfortunately, they're not as safe. So if one of these cells were to go into thermal runaway, it's fairly reactive. Now, the cells that are being used primarily for the electric vehicle industry these days are the NMC graphite, which is here in the middle. And so that's the nickel, manganese, cobalt with a graphite anode. You can see it has fairly good metrics across the board. One metric that it suffers at is safety slightly, and also the future supply. And that's because of the cobalt that's used in the system itself. I'm sure that many of you know cobalt is primarily sourced from the Democratic Republic of Congo. Just for your reference, anytime they have democratic in the name, that typically means that they're not. And because of that, the source of cobalt from the Democratic Republic of Congo is suspect. And unfortunately, China has actually acquired most of the rights to the cobalt that's being produced from the DMC. And so because of that, many of the large battery manufacturers such as LG, Samsung, Sony are actually trying to reduce the cobalt content in their cells, and we'll get on that a little bit later. Now, what's known as one of the safer technologies out there is lithium titanate oxide, which is here on the right, or LTO, and combining that with an NMC. The great thing is it's a safe technology. It has a really good lifetime, but unfortunately, the energy density is not so good. And so technologies like this are being considered for stationary applications because we want to be able to have long cycle life. We want them to be very safe because they're going to be incorporated into buildings in the future. And so those are the three primary technologies we have. And one other thing I just wanted to highlight is Once again, the highest energy density cells are here on the left, and the lower energy density cells are here on the right. Now, cost. What are we going to be doing about cost? Here you can see the cost from 2005 and the anticipated cost down to 2030. Back in 2005, the cost per kilowatt hour was around $1,400 per kilowatt hour. The DOE cost target, or the ultimate goal in 2028, is going to be around $80 per kilowatt hour for the systems that are coming out. One thing that should be noted with the decrease in cost from 2005 all the way down to 2020 is that the cost has primarily been reduced because of the engineering of the battery systems itself. In other words, they made improvements to the separator. Since 2005, they decreased the separator thickness from about 40 microns to even 10 microns these days. They've decreased the size of the current collectors, so the copper and the aluminum current collectors within the cell, they've been able to decrease it. And so that's what's responsible for most of the cost savings that you see here. It's not really chemistry dependent, it's more actually engineering dependent. And but now, unfortunately, we've gotten to the point that reducing a separator thickness from, let's say, 10 microns down to 8 microns is great, but it really doesn't save you a lot of space in the battery. So the cost targets, in order to be able to meet these lower cost targets, what we need to do is we need to go to new chemistries on the market. And how are we going to do that? This is kind of a graphic of where we were, where we are, and where we're going. Where we were, or where we are, is graphite and high voltage NMC. That was around $500 per kilowatt hour. We're now working on high voltage NMC and combining silicon with graphite on the anode. That will allow us to get down to about, let's say, $100 to $150 per kilowatt hour. But eventually, in order to be able to meet the Department of Energy cost target of $80 per kilowatt hour, we're going to have to be able to go to new lithium metal and lithium sulfur cathodes on the system today. So I know the slide is very busy, but I get a lot of positive comments on it because this kind of outlines the direction of the cathode, anode, and electrolyte research that's out there today. So for the cathodes, the present is NMC, so nickel, manganese, cobalt, and it's the material of choice for most electric vehicles, as I said before. However, the short-term research is focused on reducing the NMC content to going from like 111, which has equal portions of nickel, manganese, and cobalt, to something like 811, which is 80% nickel, 10% manganese, and 10% cobalt. We're basically going to higher nickel systems, but unfortunately, that leads to stability and safety concerns. The long-term research where we want to be is developing lithium sulfur systems, and the energy density for that is around 500 watt-hours per kilogram. For reference, the NMC technologies is typically around 200 watt-hours per kilogram, depending on which one that you're talking about. The long-term research in lithium sulfur, is focused on getting higher and higher energy density systems, but lithium sulfur technologies suffer from polysulfide formation and migration, which actually limits their cycle life. So that's what we're working on the cathode. On the anode, the present, basically graphite is king. Graphite is the anode of choice. The short-term research is combining silicon with graphite in order to be able to increase the energy density. And LG, Samsung, Sony, many of the major battery manufacturers that are out there today have already done this to be able to increase the energy content or the specific energy of their cells. But the long-term research for anode technology is going to be focusing on 100% silicon. Silicon has greater than 1,000 watt-hours per kilogram, but a couple issues need to be addressed when working with silicon systems. And one is the consumption of lithium when the battery is first formed. And that's basically the solid electrolyte interface. When we first form a cell with silicon in it, a lot of the lithium is consumed in order to be able to form that SEI. And unfortunately, then it's not used in the cycling of the battery system. We also have to work with silicon systems in the fact that they have a volumetric expansion by a factor of 3. If you can imagine it, your anode growing from a discharge state to a charge state by a factor of 3, that's going to be kind of difficult to contain in a battery system. So So what we're doing is we're going to silicon nanoparticles and increasing the porosity in order to be able to address that. The eventual long-term research is going to be leading towards lithium metal. Obviously, you can't have any more dense of a lithium reservoir than a lithium metal. But the one thing that we're going to have to work on before incorporating lithium metal into battery systems is their dendritic growth. Dendrites can grow from the anode or from the lithium metal to the cathode. And when they do that, they pierce the separator and cause an internal short circuit within the cell. So in order to be able to prevent that from happening, what we're doing is we're working on solid state electrolytes. And this solid state electrolyte will prevent that dendritic growth or the dendrite from the anode to the cathode and prevent these cells from going into thermal runaway. However, most of the solid state electrolytes that are on the market today are being produced. They're oxide and sulfide based systems, but unfortunately they're being produced in a batch process. They're not being produced in a roll-to-roll process and basically meters per second. And so that's one of the big barriers with getting solid-state electrolytes onto the market today. And finally, the other major component for a lithium-ion system is electrolytes. Right now, and what's been used for about the past 20 years is what's called the Gen 2 electrolyte. And that's a combination of ethylene carbonate and ethyl methyl carbonate. And it's those two solvents are combined with 1.2 molar of LiPF6 salt. Now, you can't tell me that 20 years ago that we just happened to luck into the best electrolyte that's out there. So basically, what we need to do is we need to improve, the performance of this electrolyte. And in particular, in order to be able to increase the energy densities of the system, we need to be able to have a liquid electrolyte that will go up to higher voltages. The Gen 2 electrolyte starts to break down at about 4.3 volts. Once you go above 4.3 volts, it breaks down, generates carbon dioxide. Unfortunately, going back to that pouch cell, that would then cause that pouch cell to blow up, and you'd lose connection between the separator and the different layers within the battery system. And so what we're trying to do here is look at high voltage carbonate electrolytes. And then the short-term research is looking at fluorinated compounds and ionic liquids. That's primarily to enable extreme fast charging. And of course, I just mentioned this, the long-term research is going towards solid-state electrolytes. But the big thing with them is that we need to increase their ionic conductivity, and as I mentioned, basically make them into a roll-to-roll process. So for those of you that are curious, this is the DOE Vehicle Technologies Battery R&D portfolio. They're working on enhanced lithium-ion graphite NMC systems on the right. You can see the metrics that I've pretty much already talked about here. But one thing that I want to highlight is that they're going towards an energy density of around 300 watt-hours per kilogram, and a cost figure for those is about $100 per kilowatt-hours. The next gen system is a silicon NMC. We feel that that technology can get to 400 watt-hours per kilogram from an energy density perspective, and the cost would be approximately $75 per kilowatt-hours. The eventual goal is to get to lithium metal, combining with NMC on the cathode or lithium sulfur on the cathode. And that projected cell energy density would be around 500 watt-hours per kilogram, and the cost would be down to about $50 per kilowatt-hour. Replacing sulfur, or replacing the nickel, the manganese, and the cobalt with sulfur, which is a very earth-abundant material, causes that cost to go down significantly. However, when you're doing this, nothing is free, and you need to consider the balance of plant. So all of the specific energy density targets that I've mentioned today so far has been on the cell. But what you need to do is you need to consider the battery system itself. So a battery system consists of a number of different cells that are connected in series and parallel. And basically what this is trying to do is give you the required energy, power, life, cost, and the mission requirements that are necessary. However, a battery is more than just the cells, and it requires a number of different subsystems in order for it to be able to work. So you have the mechanical hardware, you have to be able to address shock, vibration, crush, and impact. You have the electrical hardware, so the wiring, the fuses, the disconnects within the battery. You also have all the wiring for the BMS, or the battery management system, within a battery pack. Just so that you guys know, in a lithium-ion battery, in order to be able to balance the cells, every single cell within a lithium-ion battery pack, you need to know the voltage of that, and you need to know the temperature throughout. In order for you to be able to, you also need to be able to control the temperature within the system itself, which requires fans, pumps, heat exchangers, or heat spreaders, flow channels, and of course, you're going to have hardware, software, controllers, sensors, and CPU. And finally, there's going to be different hardware that's going to be incorporated into the battery pack from a safety perspective. So other attributes to consider are manufacturing, recycling, maintenance, and repair. But basically, what does this do to your energy density of the system? All those subsystems that I just mentioned, they add volume and weight to your battery pack. And because of that, you're going to reduce your specific energy density of your system. So just for reference, current electric vehicles, the mass of the cells of the battery systems is around 50%, 50 to 65%, which reduces the energy density significantly. So 50% of the mass of the battery pack is around is the cell weight. The other 50% is all those ancillary systems that I just mentioned. NASA's spacesuit battery is probably one of the best when it comes to specific energy density of the pack itself, and that does around 70%. However, the cost that's associated with generating that type of system can be done for space applications, because obviously bringing weight into space is very expensive. However, that's not, we can't actually justify those costs for electric vehicles, and it will be a little bit difficult to justify for Evtol applications. So to give you an idea, if I have a battery system that has a cell at 50 watt hours per kilogram, the best that I would be able to do is probably get, you know, basically the penalty associated with combining that into a pack would cause the energy density to go down to around 375 to 400 watt hours per kilogram. And to be honest with you, practically that 500 watt hour kilogram per cell, once I incorporate it into the pack, that system will be down to about 350 watt hours per kilogram. So when you're developing battery systems, you need to take this into consideration. If you don't do this, obviously there's going to be, you're not going to be able to meet the metrics for your particular application. Now, 3 different priorities that I want to touch on. The first would be extreme fast charging. Extreme fast charging is very important from the EV industry. I also know that it's going to be important for the Evtol industry too. This particular slide goes over why it's important for electric vehicles. Basically, one of the primary reasons why we're pursuing extreme fast charging for battery technologies is that consumers cite the number one reason for consumers not buying an electric vehicle is the fact of range anxiety. And so we want to be able to address that and develop DC fast charging. So you can see here the graph on the right. If we do no DC fast charging events, we're only able to travel about 8,000 electric vehicle miles during the year. However, if we increase those DC fast charging events to 1 to 5%, we actually increase the electric vehicle miles by 25%. So we go from 8,000 to 10,000 electric vehicle miles traveled per year. But what does this translate into in power and time? And so if you look at the table here on the left, if we have a level 1 charger, which is just 110 or 120 volt outlet that we have in our homes, to be able to get 200 miles back into the vehicle, it'll take 2,100 minutes of charging in order to be able to do that. If we do DC fast charging at 50 kilowatts, it'll take about 60 minutes. However, if we go to extreme fast charging or 1,000 volts at 400 kilowatts, it's only going to take about 7.5 minutes to charge that battery pack for 200 miles. And this is somewhat equivalent to the time that it takes for you to fill gasoline into your ICE engine. However, unfortunately, extreme fast charging comes with its challenges and difficulties. One of the biggest difficulties that are out there today is the lithium plating that occurs in higher energy density cells. So we talked about the energy cell and the power cell. The anode that you see here on the left is actually a power cell. The anode that you see here on the right is an energy cell. And what you can see here is this gray or white deposit within on the cells. And that's actually lithium that's not intercalating into the graphite during charging. Rather, that's lithium that's plating onto the surface of the anode material. And so what's happening is that lithium is growing from the anode. Once again, it's forming a dendrite growing from the anode and going to the cathode and can cause a short circuit. Other issues with lithium plating are that you're going to be decreasing the capacity of the cell. And so this is something that's very important for us to be able to address. Sorry about that. One other issue with extreme fast charging of lithium batteries is that there's going to be a lot of heat that's going to be generated. The great thing about lithium batteries is that have very high coulombic efficiencies. That basically leads to their very high cycle life. However, they also produce heat. So under extreme fast charging conditions, they're going to be doing joule heating, which is producing about 30 to 40% of the heat. There's also going to be heat generation from the electrode reaction. So this is the ionic transport and the electrolyte. And this is going to be generating 60% of the heat. And then finally, there's going to be entropic heat generation within the cell that typically for extreme fast charging conditions is going to be less than 5%. Now, getting back to the comparison of energy and power cells, these are two cells that have the same chemistry, so NMC graphite. The red curve is the power cell, and the blue curve is the energy cell. And you can see here, this is the heat efficiency for the two. For a 2C rate for the HEV power cell, we actually have efficiencies of around 99%. However, the 2C discharge rates for an energy cell, our heat efficiency is approaching around 90%. So think about it. If I'm charging the cell at 400 kilowatts and I have a 10% heat load on that system, basically I'm generating 40 kilowatts of heat. And somehow I'm going to have to be able to manage that. So what we want to do with, to be able to enable extreme fast charging is taking that heat efficiency curve of the energy system and make it much more like the power cell that you see here. The next topic that I'd like to talk about a little bit and touch on is the life and the degradation of lithium systems. Obviously, this is important for all applications in which lithium batteries are being used. In order to be able to understand how life affects the system and what the degradation mechanisms are, typically what we do is we combine the physical fade mechanisms and the physics equations that you see here on the right with data that you see here in the lower left. And we combine those two to be able to understand what the degradation mechanisms are within the cell. Some of those will be SEI growth and damage, particle fracture. The particle fracture then leads to electrical isolation. We've touched on the electrolyte decomposition, where we're actually decomposing the electrolyte and producing carbon dioxide within the cell. Therefore, we get gas generation and delamination, and of course, lithium plating, we talked about that. All of these issues contribute to decreasing the cycle life of the cell. And this here is a graphic that we did for a stationary application where we're testing the cell in the upper left-hand corner. And this is data that we're looking at for both storage and cycle life. And basically what this data comes down to is this curve in the lower right-hand corner here. And the curve is showing you two things. As you increase the temperature, you decrease the cycle life. And as you increase the usage range of the battery itself, you actually decrease the cycle life also. So those are the two primary levers that are going to be affecting battery life within the cells, what temperature you keep it at, and what depth of discharge in which you discharge that particular cell. And finally, safety, I wanted to touch on that. NREL has worked very closely over the last 12 years with NASA on a number of different designs. We started looking at safety for the spacesuit battery, for the spacesuits, for the astronaut spacesuits and the International Space Station. What we did is we took that knowledge and we've applied it to the X-57, which is an electric vehicle, electric Evtol vehicle that's being produced by NASA. And what we're trying to do is we're taking all of the safety lessons from the astronaut's battery and the past testing that we've done and incorporated into new module designs. So the X57 battery consists of a 320 cell module, it should be as no surprise here to anyone. The first time that we actually activated or basically sent a cell into thermal runaway, we actually get propagation throughout the pack. And this was a very good lessons learned in order to be able to reduce that. The EPA that we did, or the destructive physical analysis that we did on this particular 320 cell module, revealed a number of problems with the design. One, the first problem we saw is that there were a lot of the 18650s that had sidewall ruptures in them. You can see the pack design here of 18650s. If you have a sidewall rupture on one of these cells, then what happens is it's clocked probably towards an adjacent cell. When that happens, the ejecta and the heat that's coming out of the cell will then cause the adjacent cell to go into thermal runaway, and then we just have full-blown thermal runaway for these particular cells. Also, what we found out when designing modules and battery packs is that the enclosure itself is very important. So the first thing that we were trying to do is trying to isolate the heat from a particular cell from going to adjacent cells, and we found that that was the wrong thing to do. And the reason why that was the wrong thing to do is because that cell heated up so much. Instead of only going to 500 and 600 degrees C, it actually went to 1,000 or 1,200 degrees C. And then that temperature causes adjacent cells to go into thermal runaway. So from those two lessons learned, what we did is we actually put protections on the sidewall, and we actually made the matrix that holds all of these 18650 cells in place. We made it conductive. So we were able to actually take the heat away from that cell and distribute it among the matrix and the adjacent cells, so that the thermal runaway that happened in a single cell didn't propagate throughout the rest of the pack. Now I want to show a video here. Hopefully it'll show up fairly well. This is the original X57 battery design, and as I said, it failed in propagation testing. What we did is we sent one cell into thermal runaway by overheating it and basically breaking down the separator. And you can see here what happened to that particular battery pack. More recent tests that we've done on this, activation of internal shorts within a battery pack, within the X57 battery pack, have actually been successful, and we've been able to limit this and prevent this from happening. So when we activate one cell, now you get smoke, you get a little bit of flame and ejecta, but it then doesn't propagate to the rest of the pack. And basically, we're going along NASA's philosophy. It's okay for a single cell to go into thermal runaway, but it's not okay for that to then propagate throughout the rest of the pack. Finally, I want to just touch on one particular topic, and this is the internal short circuits that we were talking about. This is very much in line with the dendrites that I referred to earlier. Basically, the dendrite that's growing from the anode to the cathode surface. Once again, anytime you get a dendrite goes from anode to cathode, you can have an internal short within it. And so NREL and NASA developed this internal short circuit technology to be able to assess what happens in internal short conditions. And we were lucky enough to partner with University College of London and Donald Finnegan to incorporate internal short circuits into cells and then look under high-speed synchrotron XRD at what happened to the cell. And so this is an 18650 that has fairly high specific energy density. This is a 3.5 amp hour cell. The specific energy density for the cell is around 300 watt hours per kilogram. And I'd like you to take note of the time in the upper left-hand corner of when this starts. So this starts at 1.65 seconds real time. And what I'll do is I'll play the video. So 1.65 seconds, just slightly after that, we activate the internal short circuit within the cell. And what you do is you see the different layers coming together, and almost immediately, within a tenth of a second, you actually see the electrode material telescoping out of the cell here. So that's what you see here is the different layers unwinding from the cell and being ejected out of the port at the top of the cell. One thing of note, and one thing that we haven't seen in the past, and I'm going to pause this video here, is you can see these different little pools of liquid. These pools of liquid are not seen at lower amperages or lower capacity cells. So when we tested cells like at 2.4, 2.5 amp hours, we actually didn't see this. But we're actually seeing it here, and this is the copper. The copper is being liquefied within the cell. And once again, we started this test at 1.65 seconds. We're now at only 1.95 seconds. So within 0.3 seconds, we've gone from room temperature to 1200 degrees C, and we've liquefied all of the aluminum within the system, and we've also liquefied the copper within the system. And most of the cell, and as I continue the video, most of the cell is actually being ejected out of the vent port at the top of the cell. So I'll let this run to completion. You see the jelly roll unwinding, ejecting out of the top. And finally here at the very end, what you'll see is a mass ejection of the rest of the material. And so what's important to consider here is that most of the material that was in the cell is no longer within the cell. And so if you have those sidewall ruptures, if you have the vent ruptures, and those are oriented towards an additional cell within the pack, more than likely that heat and that thermal mass is actually going to cause that cell to go into thermal runaway. And so what we're trying to do is prevent that from happening. And again, our total philosophy when it comes to this is it's okay for a single cell to go into thermal runaway, but it's not okay to propagate throughout the pack. And with that, I'd like to acknowledge the Department of Energy, in particular the Vehicle Technologies Office. A lot of this research was sponsored by Dave Howell, Brian Cunningham, and Sam Gillard. And I'd like to acknowledge those at NREL and NASA who contributed to much of this work that I presented to you today. And finally, thank you. And I'll take any questions at this time.
Yeah, for sure, Matt. This is thrilling. That was a great presentation and super enlightening for us. I have a few questions here, and then I'd love if the audience would put some up in the Q&A as well, and I'll ask them for you. One thing I was interested in, just when you were talking about the 3 research areas for NREL, if you could go into timeline a little bit. Is it an issue of basic research that needs to be done, or manufacturing research, commercializing those lithium metal batteries? What do you see as the main barriers there?
So to be able to get to the silicon and to the lithium sulfur systems, there really has to be some fundamental research on how do you create those chemistries. So, you know, how do you create the silicon particles so that you can take the 300% expansion and contraction. On the lithium sulfur technologies, so the lithium cathode that's coming up, the lithium metal, that again is going to be fundamental research where you're looking at preventing dendritic growth and basically coming up with some type of solid state electrolyte. Now, once that's done, we are going to have to go into the manufacturing phases. As I indicated, like the solid state electrolytes, they are primarily produced under a batch process right now. And we need to be able to, in order for these to be commercially available, we need to be able to do it on a roll-to-roll basis. So really the answer to your question is both. We still have a lot of fundamental research to address, but once those barriers are overcome, then we'll actually be able to get into the manufacturing side of things.
Yeah, for sure. And I know a timeline is always difficult to answer there, but we see this year trend with battery growth. Do you see this continuing? Do you see jumps happening in the near future? I mean, 5-10 years? Just your comments on that, from an expert on that trend.
So silicon systems are already being incorporated into cells right now, but typically that's only on the 5 to 10% silicon. The rest is graphite. And unfortunately, that decreases the cycle life, perhaps by a factor of 2, just by incorporating that small amount of silicon. So in order for us to be able to get up to 100% silicon and match 5,000 cycles, that will be, 5 years down the road, I would say. But right now, we have been able to address a lot of the cycle life issues, if you consider 1,000 cycles good for silicon systems. So we've been able to do that. So we're able to get 1,000 cycles out of silicon systems, but really what we're gearing towards in the future is to be able to get up to 2,000, 3,000, 4,000, 5,000 cycles, and that's not going to be happening until another 3 to 5 years down the road. For the lithium sulfur and the lithium metal systems, the time frame for that is probably on the 7 to 10 year time frame, where we'll start getting reasonably good cycle life and be able to start incorporating that into cells.
Yeah, for sure. Do you think the cycle life is a key thing, or we can start looking at batteries that reach a cost that are easily replaceable?
And that's a very good point. That's something that we have to, take into consideration. And I know a lot of the interactions I've had with Evtol technologies that people are okay with 1,000, cycles as long as the cost is at a certain price point, so that they can actually be cost effectively incorporated into Evtol vehicles. So there is that. There's the balance between cost and cycle life. Obviously, as you go to these technologies, these future technologies, the cost is going to go down. And if it's down enough and you're willing to accept that cycle life for that cost, then that's something that needs to be taken into consideration.
Yeah, do you see issues from a supply chain perspective with disposing of batteries? I know a lot of folks are looking at using them kind of for ground storage and at the recharge sites after they'd actually take them off the vehicle. But do you see long-term issues with that disposal?
I do. So in particular with the technologies that are being used right now, so the NMC technology, so nickel, manganese, cobalt, in particular the cobalt, we want to be able to recycle, that and capture that cobalt material so we can reuse it for whether it be battery technologies or other applications. So that's going to be very important. But in the future, when we're starting to get to lithium sulfur batteries, sulfur obviously is a toxic material. You don't want to have a lot of that in your landfill. You don't want to have that in your water. So that's going to be very important from a recycling perspective, those future technologies. One thing I'd like to note that from a recycling perspective, typically right now only about 5%, actually probably less, of lithium batteries is recycled present day. And that's something that we need to increase. And one of the biggest problems with recycling lithium batteries is all those different lithium chemistries that I was talking about. So you don't necessarily want to recycle NMC batteries with lithium iron phosphate or LTO batteries. What you need to do is be able to separate those out, and being able to do that in a cost-effective way is difficult. The lead acid battery has been able to do it because they really only have lead and lead oxide. So one electrode is lead, the other is lead oxide. It's fairly easy to recycle that.
Yeah, for sure. No, that was all great. And I appreciate you coming on the talk. I just wanted to ask you a little bit about NREL activities, how folks could interact with you guys, what your key takeaway or ask for the attendees are working in the space, and also a little bit on the STTR topic and would you guys be open to partnering with folks as the research institution?
So definitely we would be open to partnering with everyone, and for the new proposals that are coming out. I guess our ask is if you saw something of interest to hear today, whether it be from the life, the degradation, the safety, or the extreme fast charging, or even investigating new chemistries, we'd be happy to partner with you.
Okay, yeah, for sure. And thanks so much for coming on, Matt. We really do appreciate it and enjoyed the talk a lot.
Yeah, thank you.
Phil, over to you to introduce Major Evans.
All right, Matt, thanks again for that wonderful discussion. Up next, we have Major Jared Evans from AFWERX Ventures, who's here to discuss in a little bit more detail the STTR process and to answer any questions you have from proposal generation and submission. Jared, take it away.
Excellent, thank you so much. I appreciate that. We're gonna take care of that weird background there. So welcome to my basement here in my home office. So with that, I'm going to share my screen and we'll jump into the presentation here. So I think a lot of you have seen what we kind of the basic of the STTR program through some of the presentations we've given previously. This is really going to go into a bit more depth in terms of what we're looking for and things that you really need to address in the proposal in order to move forward. There we go. Okay, so this slide should look familiar. The solicitation that is out on the street, the X20D solicitation that is out currently being solicited, is for phase 1 only, right? It's open to any eligible small business, like we've talked about. You know, we don't have to ask for you specifically to come and be part of the system. You know, we've heard a variety of presentations, to include the one just previous to this, that talks about some challenges, whether it be battery recycling or, you know, some of the other challenges in that tech sector. And, you know, those things are immediately relevant to what we're doing here. So you don't have to be a flying car, you know, actual flying vehicle manufacturer. You can be lots of different things that have some relevance to that tech space. And we want to talk to you, whether it's safety, whether it's some of the enabling technologies or what have you. So that's important. You can see there's much more into the process, right? Later on, we'll have phase 2 instructions that are published. Later on, we'll have StratFi's instructions that are published for this event. But what you should be responding to and proposing is your phase 1 specifically. Okay, so what goes into a proposal, right? We've kind of boiled it down here a little bit. There's 6 volumes, 1, 2, 3, 4, 5, 6, like you can see on the screen. The first is your basic information, SAM and DUNS and cage numbers. It'll ask for abstracts and a whole bunch of yes or no questions. That speaks to the registration piece that we've talked about previously that needs to happen prior to a successful submission. When you move into volume 2 is the technical side of the world. So, right, so there's a maximum of 25 slides. The template that we provided in the solicitation, right, there's direction in the solicitation of what we're looking for. There are 12 no kidding required slides. There are 9 that are required above and beyond that, that are as applicable to your concept. And then the others are elective, right? So you can beef up sections that you think need to be covered at more depth. You can also add more information, maybe that we didn't ask for specifically. So that's important as well. You'll be asked for a work plan that's non-proprietary. You can see more direction about that in the solicitation itself. And then there'll be a template with the required info on the website, right? So we have the technical slides, that 25 slide volume with more detail on the team up page of the Agility Prime website. Okay. Also, one thing I haven't mentioned is that if you don't have the solicitation open, you may navigate over to the team up page and grab the solicitation, open those, and then we can kind of walk through this together, and you can ask more questions that you need to. But while that's going on, we'll continue on here. Volume 3 is the cost volume, right? So you'll notice it's you know, it's akin to applying for a job where you put in your resume, and then the next screen is them asking for you to type all that stuff out into individual fields, unfortunately. So this cost volume is where you type in your cost information into pre-formatted spaces, right? We'll talk about in volume 5 that you can put in a document with that cost information in your own format. But this volume 3 is specifically system generated. Or system consolidated, maybe is a better way of saying that. Volume 4 is the commercialization program. You know, there's a listed website in the solicitation, and you follow the direction. It's fairly straightforward. You know, you don't necessarily have to have a score, and many of you won't if you haven't been in working with SBIRs or STTRs in the past, and that's totally okay. So that's it's important to know that if you don't have a score, that can be certainly fine. There's no issue with that whatsoever. Volume 5 is supporting documentation. The additional cost information that again is in your preferred format. You can have a letter from your research institution that says, hey, you know, we have an agreement. The resumes for key personnel, the funding agreement, certification, and other documents that you would like to input, right? So that's fairly open-ended in terms of what you put into that particular part of the system. Volume 6 is simply the fraud, waste, and abuse training that everyone has to complete. One of the things that I wanted to touch on here is that, and we'll speak to this here in just a moment, is also consistency, right? So your cost volume needs to add up to the same amount as what is listed in your work plan, right? In your work plan, you have certain things that you said you're going to do and the deliverable cost associated with that. Those need to add up to your total cost that is put in, that is just listed in volume 1. They'll be asking for your top line dollar value. And then volume 3, they'll ask for kind of the breakdown, right? So those total costs all need to add up. That sounds simple, but it's important to make sure that that helps, or make sure that those all line up. We have gotten a couple questions about MOUs and their necessity to be included now. So if you have an MOU, if you have a letter of support of some kind, whether it's from a research institution or another business or investors or Air Force folks, right? That's all great, but that is not required for this phase 1, right? The MOUs that you think of from a defense market or from the defense customers will be required, notating required in phase 2, but not for phase 1. So I just want to make sure that that's clear as well. Okay, so again, this slide should look familiar. These are non-negotiables. I'm gonna kind of speed through here, but I want to make sure to hit a couple really key points. If you come to the table and you as the small business are not completing at least 40% of the work plan, and that 40% of that contract value is going to you directly, it's not going to work out, right? That's you tie our hands there. And the same goes for the research institution, right? If you come to the table and your research institution constitutes 29.9% of your total contract value, we cannot award, right? So you really have to be very cognizant of those percentages and making sure that those costs line up across the board, right? So you tie our hands if that's not just so. Again, we talked about this is for phase 1 only with those maximums there. If you come in and ask for 175K, we won't be able to evaluate you, right? If you come in with a maximum contract length of 7 months, we won't be able to evaluate you, right? So please help us help you in this regard. Complete proposals must be submitted through the system, through the DSIP system. We cannot take anything over email, right? Again, that's not something that we really have a choice on, right? In order to make sure this is all being handled fair and equitably, we have to make sure we use this common system. We'll talk about this again, but this must be RDT&E activity, right? It doesn't necessarily have to, you don't necessarily have to be doing RDT&E work to a current commercial system, but what you have to be proposing must be RDT&E in nature, and we'll talk more about that as well. We talked about the training that's there in volume 6. That's a non-negotiable as well. And if you don't check these boxes on the way through, then they just won't be evaluated. There's a checklist that's included in this solicitation itself that outlines this further, but I want to make sure that we hit that in this form as well. Okay, so we talked about some of the non-negotiable. We're also going to talk about some of the trip hazards here. That folks, for one reason or another, that seems to hold people up when they put in proposals. First of all, do the simple things well, right? You need to meet the statutory eligibility requirement and the cost sharing thresholds, right? We talked through those a little bit, but I want to make sure that we continue to foot stomp those as we go through. It's a simple yes or no question that we have to complete, and if you're on the wrong side of that, there's just not any room for negotiation. Okay. Be consistent. I've mentioned being consistent across cost, but that also includes work plan and your overall messaging, right? If in one part of the proposal or the abstract you say you're going to do X, and later on you say, well, we're really going to do Y, right? It raises questions and it makes it difficult to evaluate effectively, to be honest. Let's see. So services versus R&D, right? This is an R&D program, ultimately, RDT&E, like we talked about, not a services. So this should not be direct procurement of your commercial product right now. We should be developing an Air Force version of your product, right? For the Air Force market, for the Agility Prime market, if you will. Another way of looking at this is a severable versus non-severable, right? Their entire training courses you know, on the government side about what this means, but ultimately, if it's something that we can just stop at any time and still get a whole lot of value out of, then that's severable, like a service, vice an objective. So if they stop a bridge construction halfway through, right, you don't get the advantages of a bridge. You know, you have to go all the way through to be to finish the job, right? And that would be more of the R&D type of aspect. Okay. So in your work plan, you need to talk through some of these this broader objectives that you're trying to achieve. Okay. We talked through R&D and not procurement. There's a lot of words there that I want to make sure that that you all see, and some questions that you can help us answer in terms of your proposal. Right. STTR does not require a commercial product to be out there and available right now for your thing. But you have to speak about how your work with the Air Force and how your Air Force product needs development based on what is being provided in the commercial space as well. Okay. Again, there's some clarifying questions that we have to answer as government folks that you can help us with. Okay. We talked about this before. If you're looking to do UAS procurement or operations, you need to account for that. Your evaluation criteria is right here, right? You need to meet the requirements of the solicitation, and you need to be rated well in these 3 evaluation criteria: commercialization, defense need, and the technical and team, right? We've talked about these before, so I won't belabor them, but it's something that you need to keep in mind when you're writing your proposals as well. And I'm going to continue to move quickly through these so we can get to the questions and answers here in just a moment. Okay, and then negotiables, right? What makes a proposal good versus just like borderline, right? And these are the things that that you can really speak to, specifically your value statement versus others, or the current solution in a certain space. Why your team is uniquely suited to address the technical and the integration risks. Okay, and you can read some of those other things and reference some of our previous briefings on this. Ultimately, 2 p.m. on August 10th, right? That's the cutoff line, right? You come in at 2:01, you're not going to have a good day. We want to make sure that we're being very clear and transparent and upfront, right? Please start your proposal early. Please complete it early. We all know that the last push puts stress on our computer and IT systems. And if something glitches and it pushes your submit time to 2:01 on August 10th, we won't be able to move forward with you. So please take that into account, and we'll go from there. So a couple things here. So we're going to move over to the Q&A, and I can read those, or Sterling can read those, whichever is most effective.
And Jared, I'll read them out to you.
Okay, and while we do these Q&As, I think it might be useful to put a couple of our polls up and kind of get a feel for the room and kind of get a feel for who we think.
For sure. So the poll should be up if you guys could put answers in. I'll read them out when we're done here. A couple questions for you, Jared.
Yep.
So these are just straight from the audience. There is conflicting info between the solicitation and slide template. Can the PI be from a partner research institution? Can that person, therefore the overall PI, be a non-citizen if they meet the requirements and are explained as directed of the solicitation?
Sure. So the PI, the principal investigator for STTR, can be primarily employed by the small business, as is the case with SBIR. But for STTR, they can also be primarily employed at the research institution as well, right? So that's an opportunity. Now, in terms of citizenship, the PI needs to be a permanent resident, right? That, i.e., a green card holder, naturalized citizen, etc. Right? You can certainly have foreign nationals work on the project, and you'll see in the solicitation there's a table where you need to declare those folks and what visas are appropriate, you know, and what their situation is. And we can talk more about that later on or over email to make sure we have, you know, everybody's clear on what that
Sure.
requires.
Do working research groups within NASA like RVLT and Evtol qualify as a research center under STTR guidelines?
That's a great question. Whoops. I've sent up or put up the slide with the research institution definition there. And if they meet that definition, then yes. Generally speaking, I know we've gotten this question on the DoD side, can AFWERX be the research institution? Being an Air Force organization, they cannot. I'm not as clear as on the NASA side of things, but this is the definition. So if they meet this, they should be able to work with the companies. And we can provide further guidance on that as well.
For sure. So the solicitation says you need an allocation of rights agreement with the research institution, but you said just earlier, just an agreement. Can you clarify?
Sure. So what we need to know on our side, right, is that you are meeting the requirements of the program, right? That you have an agreement with the university or research institution, right? We don't need to see that subcontract. If there are allocation of rights that says, hey, you know, the university says they own such and such, and we agree to that, then you can certainly, then please do communicate that. That helps us in our, you know, in general IP issues if they ever come up, just to be clear on that. But generally speaking, we just need to know that we need some kind of acknowledgement that the university or the research institution is supporting and is part of this process as they need to be. So that's all. That's more part of us making sure that the requirements of the program are being met, and less evaluating your relationship with that research institution, if that makes sense.
So someone's asking about, is it beneficial to include the MOUs with the phase one? I think you said that yes, it is.
Sure. Yeah, I think it speaks to not only the defense need, but also the commercial side. And so if you would like to speak to that through an MOU, and then that's great.
Yeah, and then someone saying they're still pending their cage code. Can they submit while it is pending?
Yeah, so cage codes we can work with. SAM we cannot, right? You need to have a SAM number, I think, in order to even get to putting in a proposal, if I understand the system correctly. Cage codes, I think we have some flexibility with. If you're not sure, I'd say put in a proposal, right? We'll tell you, you know, it will come out if we're not able to work with you. But if you're ever in doubt about something like that, you know, you've got everything lined up except for the cage code. We can certainly see if that's something that we can flex on.
Yeah, for sure. And then earlier you were talking about volume 4, the company commercialization report. I'm getting a couple questions here saying that it's not required for X20D. Is that correct?
When I looked in this solicitation last evening, it did have the commercialization report in there, but regardless of what I say in any of these presentations, the solicitation is key, right? So if at any point there's conflicting information, please do follow the solicitation. And if there's questions, we can certainly take those and run those to ground. So I will take that note just to ensure we have the right, we're pushing out the right information.
Yeah, for sure. So we have a few more questions real quickly. I'd like to go over the polls just for everyone's essay, and then we'll switch over to Dennis for the last few minutes here. So how many proposals would you expect to submit? 25 for 1, 12 for 2, and 4 for 3. So about 50 maybe there total. And then 70% of people have found a quality research partner, and 29% are still looking.
Okay, no, that's great information. I think our following presenters may be able to assist with that. Oh, perfect. Thanks for pushing those results out.
Yeah, for sure. And so we'll go over to Phil to introduce our final presenter, Dennis. And I think he can help you guys who are still with questions on your proposal there. A lot of those questions he can answer you with, and also help with the matchmaking. So thank you, Major Evans. We appreciate you being here with us again.
Yeah, absolutely. And I did notice one question in the chat window here talking about being more of a phase 2 level. With STTR, there is no direct to phase 2. So if you want to work with Agility Prime through these small business programs, like this is it, right? This is your chance to jump into the fray and into the pipeline. So even if you're a little farther along, this is the gateway. So please keep that in mind, and we look forward to seeing everyone's proposals here in a couple weeks.
Awesome. Hey, thanks, Jared. Today's final panelist is here to add to the STTR discussion. We have Dennis Anderst from the Wright Institute, a nonprofit in Ohio that works as consultants helping companies generate their proposals as well as matchmaking them with universities. So Dennis, thanks again for being here.
Major Han, thanks for having me. Sterling, if you could project the slides for me, that'd be good. We're actually the APEX program, Academic Partnership Engagement Experiment, and it's done through the Wright State Applied Research Corporation here in Ohio. And we're actually funded by the Air Force to help with small businesses and universities and research institutions partner and go after STTRs. We actually have funding to support that activity. Next slide, Sterling. So as Major Evans said, you can't foot stomp enough. Make sure that whatever you do in this proposal is you write to the evaluation criteria. We've seen in the past that folks don't do that, and they actually don't win the contract. The other thing that Major Evans said that I want to foot stomp is the fact that they've got a checklist in the RFP, request for proposals. Make sure you follow that religiously. And as he also said, is if there's a conflict, always fall back to the solicitation. If you could do the next slide, Sterling. Next slide. So the, I'm going to jump ahead in here until we get the slides moving. So APEX is set up, and we've actually been coaching roughly, I think there's about 50, 60 companies and institutions that we've been interacting with. And really what we do is if you're a research institution, you're looking for a small business, we'll try to help that connection and make that connection made. Same thing if you're a small business looking for a research entity, we'll help look for a partner. And then what we'll do is help educate you in the process of actually doing a competitive proposal and get that submitted. However, there's only 10 days. If you go to the next slide, Sterling, so we're somewhat time constrained. And if you look here, what we do is we try to help you demystify the process. If there's registration requirements like Major Evans talked about, we'll help you through that if it's not too late. And we'll also do a solicitation adherence review for you. We've been doing group briefings too on how to do the cost volume, how to do the commercialization strategy. We will do those again before August 10th. And at the top of the page here, you've got our contact. It's apex@Wright Research. It's a -research.org. Just reach out to us, and we will. I've got people ready and waiting to assist you in this process. We'll help review the strategy. The other thing we've done is we've actually been talking to some of the platform developers for Agility Prime, and we understand what their needs are. So we'll help you demystify that a bit if you're trying to tie it back to what the platform developers are needing. And we've got a set of analytics available that if you've got a really tough problem that you're looking for help on, we'll use those analytics to try to find you an optimum partner either in the region where you live or somewhere else in the country. And we've actually done that over the last 10 days, is put multiple folks together across different parts of the country. So we're here. It's not a fee for service. We're free. We're funded by the Air Force Small Business Office to provide this service, specifically with STTRs, because our pedigree and background is small businesses working with academic institutions. We know how that works and the challenges with that sometimes. So, but we're here to assist in the process. Next slide, Sterling. These are just some of the technology areas. We've got experts. We typically do this with consultants that we've got spread out across the country. But these are just some of the examples of the technologies that we do support. At the bottom of the page, it's here, we inform. We don't write the proposal. You've got to write the proposal. But we will help you to ensure compliance as best possible. Next slide, Sterling. These are items that we've collected from some of the platform developers. So if you look at some of the leading ones across the country, they've identified these as particular technology needs. So in some cases, what we've done is taken the small business and connected them to the platform developers to make sure everything's tied together. But I provided this to you, and if you are interested in getting connected to a platform developer that we're connected with, feel free to reach out through the points of contact that we've got here at the end of the presentation. Next slide, Sterling. So these are the points of contact. Really, the thing to do, as Major Evans said, is follow the checklist. Make sure you have all the things that are compliant in that proposal. Also write the evaluation criteria, make it easy for the evaluators to review it. These folks on this screen are all available to assist, as well as reach out to me and I'll help connect. But we've got folks set up to provide support to try to get as many of you set up either as partners or training to improve your probability of success on this. So that's all I've got today, Major Han, and I'll open it up for questions.
Yeah, for sure. Thanks, Dennis. It was great hearing from you again. Let me go through the questions here and see if we have any specifically for you. Yeah, can you discuss intellectual property ownership, licensing, and royalties as they apply for the proposals?
Good, really good question, Sterling. That actually is part of what we do, is help the institutions understand how to set those arrangements up. And we've got experts that understand university IP as well as company IP and will help facilitate that process.
Yeah, and then just another one that I was asking about the cost. We just reiterate that the cost is no cost for companies, right, Dennis?
That is correct. We're a free service. We're funded by the Air Force to provide this service. We're a new PIA, Partnership Intermediary Agreement. We sit in Dayton, but we got folks spread out all over the country to support you. And we're here to basically help you through this process.
Yeah, for sure. So as we wrap up here, I think that's most of the questions answered. If you have others, feel free to email Dennis or Major Evans, and they'll help you out. I think we're really looking forward to getting all the proposals in. Phil, do you want to close us out here?
Thanks, Sterling. And thanks, Dennis, and the rest of the panelists for their time today. Dennis, your organization is such a great resource for all the companies and something that everyone needs to definitely take advantage of. So please reach out. Please reach out to Dennis. To kind of close things up, as a reminder, August 10th, have your proposals in, and we'll be looking for everyone. We'll be looking to see everyone again at our next webinar, which will be in 2 weeks from today. All right, thanks again, everyone.